If your experience with databases stretches before the proliferation of cloud platforms as mine does, then when you think of traditional databases, you think of relational databases, such as SQL Server. Relational databases were, and still are, popular for on-premises applications that deal with a relatively small amount of data compared to what cloud platforms contend with. But since cloud solutions have proliferated the landscape, and applications are commonly running not on-premises, but on distributed mobile platforms such as phones, NoSQL databases, which has become a term meaning any non-relational database, have become the standard for distributed systems, such as social media platforms. This is because NoSQL is more adept than standard relational databases at handling big data, meaning data on the range of terabytes and bigger. But what exactly is NoSQL, and how does it compare to traditional relational databases? In this video, I'm going to explain what NoSQL is and how it's commonly used. I'll touch on how NoSQL or non-relational databases compare with relational databases and what this means for big data applications. I'll start by giving a functional definition of relational and non-relational or NoSQL databases. A relational database, think SQL Server, has a well-defined schema consisting of databases and tables that need to be strictly defined before data can even be stored. What's more, if the data coming into the database does not conform to this schema, then it cannot be stored. Non-relational or NoSQL databases, on the other hand, do not have a formal schema for their data. For example, blob storage, one example of non-relational or NoSQL storage, can store binary files of any type. Think pictures, videos, text files, and applications. Even in the case where there is the concept of a table, such as in NoSQL table storage, there's no set schema for the table, meaning the records don't have predefined fields. In Azure table storage, for example, each record of a table is stored as a JSON object and may have completely different fields from other records in the table. So what are the benefits of this schemaless approach? Well, it offers agility in that it supports the fast release cycle of agile approaches to development. Because unlike with a relational database, schema changes in the data don't have to be disruptive. It offers great flexibility when designing. Any agreed upon schema can be changed by developers between versions, and the database can handle it. And NoSQL databases scale to big data very nicely. They tend to have much faster writes than relational databases that have to adhere to an inflexible schema, and so have to check the schema rules when writing data. NoSQL databases inherently support changing data coming into the system because they're flexible on the schema of the data. Imagine real-time records coming from a temperature device. Now imagine the device is replaced, and the replacement sends records with a different format. A relational database could not handle this because the new records would not adhere to the strict schema, but a NoSQL database could continue to collect the new data. NoSQL databases are more performant in general, mainly because they can ingest data without doing a lot of checks on it, and it's also possible to decouple the writing of data from the reading of it, so the two different functions don't slow one another down. They also support high availability. They can be easily replicated. In fact, data replication, something that is usually avoided in relational databases, is used as a strategy to speed systems up with NoSQL. The main caveat here is that relational databases are more immediately consistent than NoSQL databases, which usually support only eventual consistency, meaning changes are reflected only after a certain delay. And because NoSQL databases are not tied down by schema rules, they don't get bogged down as much as relational databases when large data sets are involved. NoSQL databases are known for handling the cloud's often staggering dataset sizes while still performing well. Here are some of the common applications for NoSQL databases. Mobile apps often use NoSQL so the apps can handle changes to data and to the app gracefully. Real-time analytics often use NoSQL databases, where the quick writing and simple lookup of a large amount of data is beneficial. NoSQL is often used for content management systems because of its flexibility on content types. It's useful for personalization systems, such as personalized online advertising initiatives, where a varied array of information is collected about a person to customize their advertising experience. Internet of Things or IoT apps often use NoSQL because they often have to collect data quickly, and the data coming from physical devices can sometimes change, as in the example I gave of a device being swapped out, and an IoT system may have to deal with that gracefully. And NoSQL is often useful for database migration because of its simplicity and scalability and flexibility in data formats. I've mentioned that NoSQL databases scale very well. NoSQL scales very well horizontally by sharding across servers, meaning that the records can be broken up and hosted in a distributed manner. This is easy specifically because NoSQL doesn't enforce schema rules on the dataset. Relational databases, on the other hand, often have complex schema rules that would be difficult to enforce across servers. There are different types of NoSQL database. A key value database has a single unique key, like a primary key in a relational database. That key uniquely references a value such as a record. Columnar databases are designed to allow quick access of columns of data instead of rows or records. And graph databases store records as nodes of a mathematical graph, with relationships called edges connecting nodes. Each of these database types stores data in its own unique way. The main commonality between all these NoSQL database types is that they don't enforce complex schema on the data, and they're designed to be efficient and therefore fast at their specific goal. So if you're looking to choose a NoSQL database, what should you be looking for? First, consider your data model. If you're storing variable records that can all be identified and retrieved via a simple key, then a key value store such as Cosmos DB or Azure Table Storage is probably suitable. If you're storing records that have variable and possibly changing relationships to one another, and you want to find records by traversing those relationships, then a graph database is a good bet. You also want to evaluate what eventual consistency will mean for your solution. Non-relational databases trade off consistency, that is, how quickly the system reflects changes, for speed and scalability. You want to consider whether a query of your database not reflecting the latest data is a make or break situation for your application. Consider how much cloud computing you'll be doing versus on-premises. NoSQL is ideal for cloud computing, but you can also find solutions that consider hybrid scenarios. Some other things you'll want to consider are how easily you can deploy and operate the solution you're looking at. NoSQL solutions vary in how easy they are to use and deploy. You'll want to consider data integration, specifically how the solution handles distributed databases, and what are its replication methods. We touched on data models. You need to make sure the solution supports all the data models you're going to want to use. You'll want to know the provider's geographic presence. For instance, if you really need to serve data in China, does the provider have the required data centers in China? And what are the guaranteed service levels? What latency and availability guarantees are offered? In today's distributed computing world, there are a myriad of ideal applications for NoSQL databases. Just a few that you've probably used are distributed gaming and e-commerce. Some things these have in common that make NoSQL shine are that they rely on big data, often flowing with high throughput, and users expect near real-time performance. By being flexible and not being tied down by complicated schema, NoSQL databases can offer super fast read and write times for such applications. And their low latency is enhanced by the fact that they can be distributed to different regions. Finally, they support replication and are more flexible regarding disaster recovery than a lot of relational databases. In this video, I'm going to be comparing and contrasting relational versus non-relational databases. It's important to realize that cloud-native apps may use relational or non-relational databases, and sometimes they use a combination of the two. Which one you use really depends on your application. Relational and non-relational databases are entirely different beasts. They're built differently and for different purposes. They store data fundamentally differently. So aspects such as your expected data throughput and the distribution of your database are going to be a factor in which one you use. They're also accessed differently. For instance, relational databases are often accessed via SQL-type queries, whereas an Azure Gremlin graph database, which is non-relational, has its own Gremlin traversal language. Application requirements are going to determine what's most appropriate. So as a cloud developer, how can you know which database system to use? To answer this, let's look at the characteristics of each. Relational databases have the benefit of having been around the longest. They've withstood the test of time for decades, so when you tell your customer their data is stored in SQL Server, they probably know that term, even if they're not highly computer literate, and they trust its reliability. Relational databases have a fixed schema. You define the schema before the data is stored, and that schema, while changeable, is not easily changeable. Changing it often involves a data migration. If your data has a very well-defined schema, it may be suitable to store it in a relational database. Application configuration, for example, is often stored in a relational database because it has a known schema and doesn't usually fall under the umbrella of big data. The SQL language is usually used to manage relational data, and it's a mature, powerful language. Relational databases typically support the ACID acronym, which stands for atomicity, consistency, isolation, and durability. If you have requirements that demand robust transactionality and immediate consistency, you may want to consider relational databases. And one of the hallmarks of relational databases that's right in the name is relations. If you have data that requires rigid sets of related tables, that fits perfectly into the relational database paradigm. Now let's look at non-relational databases. Non-relational databases are known for their high performance for both reading and writing. This is what makes them so good for real-time applications in the cloud. Compare your requirements against what NoSQL databases have to offer. Some NoSQL database types work in ways suitable to certain implementations. For example, a NoSQL graph database is specifically designed for data with flexible relationships between nodes. Non-relational databases are typically easier to use than relational. You can store data in them, for instance, without defining a rigid schema ahead of time. So if it's beneficial for you to just start collecting data immediately, non-relational solutions can support that. Non-relational databases, by their simpler design, are highly scalable, which plays well for big data scenarios. And non-relational databases are resilient. If the data schema changes up, for instance, non-relational databases can roll with the punches and store your data regardless. They support distributed replication to minimize loss of data. When comparing relational and non-relational databases for your needs, consider the CAP theorem. CAP is an acronym which stands for consistency, which means that queries reflect the latest data, availability, meaning the database responds quickly even if its data is stale, and partition tolerance, meaning that if one part of the database fails, the rest of it can keep functioning. The CAP theorem states that any database can excel in 2 of 3 of these aspects, but not all 3 at once. Relational databases are often good at consistency. They always return latest data. And availability. The system will respond promptly to a query, but relational databases are not good at partition tolerance. For instance, if one table fails, the interrelated schema usually fails and other tables cannot be effectively queried. For this reason, relational databases are usually not highly distributed, and instead typically run on one server, and if you want to scale them, you add resources to scale that server up. Non-relational databases are usually highly available, and they can actually offer high partition tolerance. They can be distributed in different regions, for instance, and if one region fails, the other region can continue to serve data. They're not so good at the consistency piece of the puzzle. Non-relational databases have come with the concept of eventual consistency, meaning there's a time during which the database might serve stale data before it becomes consistent. This is largely a trade-off for the ability to be distributed. So again, you should be aware of these realities, and which you choose will depend on your specific requirements. Over the years, relational databases have evolved a few tricks to improve reliability and performance. Many relational databases offer built-in replication, where the database is replicated, and when changes are made to one master copy, all replicated copies receive the same changes. This way, if the active copy fails, say there's a drive failure, the system can fail over to one of the available replicated copies. This can also build some concurrency into reads, as concurrent reads can be performed on different copies, speeding up performance. Relational databases can also be horizontally partitioned to some degree by sharding the tables, meaning breaking them up among servers. However, it should be noted that highly relational data, which requires many joins for queries, is going to perform poorly on a horizontally partitioned database, as there may be excessive communication required between servers. Now let's look at NoSQL databases. Non-relational or NoSQL databases excel at scaling out horizontally, that is, having their data spread out onto multiple servers for parallel processing. This is because of their simple design that's not based on excessive relationships between data objects. Because of this scalability, they also excel at availability across geographical regions, as the database contents can be easily replicated to different locations. This also allows for massive redundancy, meaning that there are many copies of the data in different server locations. Redundancy leads to fault tolerance, since when a database fails, the system can fail over to another database. All of this comes at a reduced cost compared to what it costs for relational databases to be implemented in a similar distributed manner. So some things to consider when looking at relational versus non-relational databases are: relational databases work best under consistent, not overly high volume workloads. They typically guarantee ACID compliance, meaning they're consistent in always returning the most recent data, and they're transaction-based, so transactions can be rolled back if they fail. They're best for highly structured data, where the structure is not always changing. They can guarantee write safety in the case of multiple concurrent writes. So if write safety is a concern, you should think about relational databases. If your queries are complex, it may signify that you have many relationships, which relational databases may serve best. If your users are all centralized geographically, so you don't require geographic distribution, relational databases might be best. Non-relational databases, on the other hand, are streamlined to handle very high volume workloads. They achieve this by not adhering to ACID guarantees. They're great for managing data that's dynamic, such as ingress data that doesn't have a strict format. They're perfect for geographic distribution. If your data does not have interrelationships, then it may be best served with non-relational databases. And queries to non-relational databases are typically simple. So if your query needs are simple, it's another possible indication to go with non-relational databases. The last topic I'll cover is Database as a Service. This is the option for a cloud provider to manage your database for you. They usually offer security, scalability, and monitoring built right in. With serverless options, you don't even have to worry about what servers your database is running on, because that's managed for you. Your database then acts as a backing service, where the database service is not part of your solution, but is simply consumed by it. These types of cloud offerings often offer just-in-time capacity, so the database capacity scales automatically when it's needed, and since this is a service, you typically pay as you go, meaning you pay only for the database storage you use. Both relational and non-relational databases are available in this model. In many ways, relational databases are designed for general use. They contain tabular schema that are meant to store a wide variety of data, and they're generally queried by a SQL-like query language. Relational databases are typically not varied for use, but are instead one-size-fits-all. Non-relational databases, on the other hand, were conceived from the start to be very requirement-specific. They don't adhere to tabular schema with rows and columns. Instead, different non-relational solutions offer very different storage models, and these are optimized for specific requirements. Moreover, they store very requirement-specific types of data and have their own ways of querying that data. As an example, Azure Blob Storage stores files that are typically accessed via a URL, while the Azure Cosmos DB Gremlin database stores text and numerical data as properties of nodes that have dynamic relationships, and the data is queried via the Gremlin traversal query language, which is quite different than SQL or Azure Blob Storage Access. In this video, we're going to look at some common non-relational databases and how they work. The first non-relational database is a document data store. Azure Cosmos DB is an example of a document data store. Basically, any database that stores its records as documents and allows you to query according to property values stored in those documents can be called a document data store. Many document data stores are designed to facilitate querying different text files, such as JSON, which may contain data in the form of named string fields, as well as fields that contain objects as data values. The document data store allows you to query for the dynamic data contained in these files. Next, there's columnar data stores. These are like relational databases in that they store in columns and rows. However, unlike relational databases, in which normalization of data is favored and data duplication minimized, columnar data stores use a denormalized approach, duplicating data in the columns of the tables for quick reference querying. Columnar data stores have the concept of column families, which are groups of columns that are typically queried together. Where in relational tables, rows are typically added as records, in columnar data stores, columns are dynamically added to column families. A columnar data store is optimized for the retrieval of whole columns, where relational databases have tables optimized for retrieval of whole rows. To achieve this optimization, data is stored in key order. By allowing sparse population of rows, this type of data store is optimal for dynamic schemas. A key value data store has records managed by a large hash table. Each record is identified in the hash table by a unique key. This single key allows for simple query, insert, and delete operations. Key value data stores are highly optimized for simple lookups because unlike relational record stores that might have many keys, this store type has only one. This simplicity makes it extremely scalable, as complex relationships don't have to be managed between records. Azure Table Storage is a good example of a key value data store. A graph data store doesn't have records. Instead, it logically organizes its data into nodes, which are objects with simple string and number properties, and edges, which are the dynamic relationships between those nodes. This models a mathematical graph, and it's best used for data where objects have various, dynamic, and possibly changing relationships. Graph queries traverse the edges to find nodes along the graph. For example, a typical graph query might query a family tree graph by looking for all children of the family who had grandparents that were named George. Azure Cosmos DB is a document data store, but it can also be used as a graph data store via its Gremlin Graph API. Next, we have the object data store, and a perfect example of this is Azure Blob Storage. Object data stores can save any object as a binary file, such as images, text files, audio and video streams, large applications, or even virtual machine disk images. Literally anything that can be stored as a binary file on disk can be stored in an object data store. Applications and services typically query for the whole objects. For instance, a website might refer to the images in an object data store to display on the website. Analysis services may also analyze these objects in clever ways. For example, an AI service might search the images in a big data object data store for images that contain faces. And finally, there are external index data stores. An example of this is Azure Search. These data stores don't store data directly, but instead manage indexes that reference data in other data stores. By optimizing only indexes to data, they can reference large volumes of data and through efficient optimizations give near real-time access. They can be configured to index data across multiple dimensions and can allow unique searches such as free text searches. While searching every file in a large database for a keyword could be very time-consuming, if an external index data store has already indexed those files by various keywords, that search becomes much faster. External index data stores can offer full text and web-based searches which are readily optimizable. Two of the most popular data formats these days for distributed systems are comma separated values, or CSV format, and JavaScript object notation, or JSON format. These two formats are commonly used when ingesting data and also when exchanging data, say between services. Both can be used to store unstructured data, where fields of the data are unknown, or semi-structured data, where the fields may follow a particular pattern, although that pattern might be flexible. JSON format allows for objects that have key-value pairs as properties. The values in the key-value pairs can be atomic types, such as strings and numbers, but can also be other complex objects. In this way, JSON can store hierarchical structures, representing complex data. These days, most coding libraries support serializing and deserializing of JSON, making it easy to take JSON data from a file to code and vice versa. JSON supports arrays or lists of objects natively, making it easier to serialize and deserialize arrays of objects. And JSON is a format that's very common in NoSQL databases. Azure's Cosmos DB stores its data in JSON files. JSON is now widely used in different facets of a system, such as representing logical formats in code. Libraries for writing APIs usually come with JSON serializers and deserializers for facilitating data flowing to the API code and back out as JSON. Because JSON is now so widely used and supported, it's used as a common exchange format between databases and other systems. Many NoSQL data stores natively use JSON format, such as Azure's NoSQL table storage. Most non-relational distributed systems support both CSV and JSON formats, although how they are most often used differs. CSV, which is compatible with Excel, is more widely used for data exchange for analytics, whereas JSON, which offers more complex data structures and is often more compact, is used for many hot data applications, such as data ingress. JSON is also used more widely to represent logical code structures, and for communication between services, say in a microservice architecture, and with API interfaces. Azure contains several offerings that work natively with CSV and JSON files. Examples are Azure Storage, which offers tabular as well as blob and file storage, and Azure Data Lake Store, which is a common big data storage that can be used for analytics purposes. There are many options to load data from either CSV or JSON into these data stores. For example, Azure Table Storage, which is part of Azure Storage, allows bulk import directly from a CSV file, and Azure Data Lake natively stores its data as JSON files, allowing you to query the JSON files as if they're records, with the name-value pairs in the JSON acting as the fields of the record. Although CSV and JSON formats are widely used and supported in cloud environments, there are a few things you should be aware of. Both are susceptible to data corruption, since they have no internal checks on structure corruption, unlike, say, some binary files that store bit sums as part of their content, which can be checked to determine if the file is corrupt. Neither CSV or JSON scale very well with big data, so if you're storing mass amounts of data in a cold storage for analysis, you might want to consider other formats, such as Parquet, that are more scalable. And even though both formats are schemaless, you may want to have a schema by convention for end consumers, such as reports or analytics applications, so they know how to read the data. For example, if you have JSON objects that contain temperature data, and you have an application that reads that data and displays a chart of the temperature over time, that application needs to know the name of the temperature property in the In this video, we're going to look at the details of non-relational data stores. To start, let's look at some typical requirements of non-relational data stores. First off, non-relational data stores tend to have either a very simple schema or no schema at all. I say some have a simple schema because in some cases, defined keys are used, which are a type of fixed schema. In any case, schema is minimized, which enables more scalability and performance. Non-relational data stores are generally non-transactional, meaning that requests to them are not batched and cannot be rolled back as a batch, but instead each request is treated separately. This facilitates distribution of databases over multiple servers, but it does mean that non-relational databases aren't necessarily ideal for applications that are highly dependent on transactionality, such as bank transaction software. Some non-relational data stores offer limited transactionality, but it's not as robust as that offered by most relational databases. And non-relational databases have simple indexes, ideally just a primary index, and if there are secondary indexes, they're simple. Again, this is for scalability, since complex indexing hampers scalability. So the first data store type we'll look at is the document data store. In a document data store, records are stored as documents, such as JSON files, and the fields of a record are the properties of the file. The document data store is denormalized. This means that documents are independent and duplicated data is not removed. For instance, if two documents both contain the same property value, that value will be duplicated because it is stored as a literal in both documents. In contrast with normalization, the duplicated literal would normally be stored once, and both documents would reference a single instance. Document data stores typically have tunable consistency. You can trade consistency for scalability. Document data stores are used to collect the exact data in the documents as is. This explains why the data is not normalized, since normalization would be a transformation of the data. Documents in a document data store have a primary key, a unique key for each document. Fields within the file, such as the properties of a JSON file, can also be indexed for faster lookup. The datum, or data in the individual files, tends to be small to medium. That is, the files are on the size range of kilobytes to megabytes. And the scale of a document data store can be very large. A single data store can typically store petabytes of data. Next, we have columnar data stores. These data stores are also denormalized, meaning that duplication of data is chosen over compressing the data by removing duplication. This is primarily for performance. Columnar data stores have a simple schema consisting of column families, or groups of columns that can be quickly accessed together. Columnar data stores use the concept of tabular data, although unlike a relational database, where records are stored as rows, in columnar data stores, the primary data object is the column. Both primary and secondary indexes may exist on a columnar data store for fast retrieval. The datum, or data records, can be medium to large. A single column can store gigabytes of data that can be retrieved in one call. Like most non-relational data stores, the scale of a columnar data store is large. The key value data store is a store with a single key for each value in the store. This is denormalized, since identical values are simply duplicated. Data is referenced via a single key. The data is considered tabular, with the key being equivalent to the primary key of a relational table. There is only one primary index for simple, very fast lookup. The datum here tends to be small. In other words, the data values are simple. This can scale to the very large petabyte range. Next is the graph data store. Unlike most non-relational data stores, this one is normalized. A graph data store contains records as nodes that are connected to one another via edges. A hierarchy is a type of graph where the nodes are the nodes of the hierarchy and the edges are the parent-child relationships, typically represented by lines. This is considered normalized because nodes can belong to several paths in the graph. In a hierarchy, a root node is included in all paths below it, and yet that node is singular and not duplicated. Consistency is guaranteed at the graph level. And as just described, this data stores graphs as nodes and edges. Each node contains a primary index, but properties within a node can also be indexed using secondary indexes. The datum, in this case being a node, is typically small on the kilobyte range, and the scale of a graph can be large in the terabyte range. Note, however, that it's not very large or petabyte range, as many other non-relational data stores are. This is primarily because of the added complexity of the normalized state. So when a graph gets too large, read latency suffers. An object data stores any type of object. Blob stores are one example. They're denormalized primarily because every object is independent. There's no consistency guarantee because it's not relevant as there are no transactions. Objects are managed in atomic actions such as create and update. Binary objects of any type can be stored in an object data store. Examples are images, videos, or even application files. Each binary object is referenced via a primary index. These object files can be large to very large. There's no reason you can't store a file that's terabytes. And the scale of the data store is very large. Blob storage is often the basis of big data sets that can be petabytes. The last data store we'll look at is the external index data store, which only stores indexes to other databases. Indexes are not typically normalized, so this is a denormalized type of data store. Consistency over transactions is an irrelevant concept here. In this case, the data store itself is a secondary index to other external data. The indexes are small in nature, usually kilobytes, and the data store itself can become large, but not usually very large, as interrelated index groups will become inefficient if they grow too large. In this video, we'll look at free-form text searching. If you've ever performed an internet search on a popular search engine like Google, then you've taken advantage of free-form text search. Basically, you can type anything in, and in the case of an internet search, internet sites are returned that best match the text you entered. Let's take a look at the steps involved in doing this. First, probably before you enter your search, the search has constructed specialized indexes that allow it to search through the data, in this case websites, in an efficient manner. Then you submit your query, which in this case is your search. The service returns a result set based on the query, and optionally, the service may highlight phrases in the found items that match your criteria or search text. Free-form text searches often face the challenge of searching a very large pool of unstructured items, and as in the Google search service, it may be expected to perform this real-time. Free-form text searches are computationally intensive. In many cases, the service is searching over an incredibly large dataset. In the case of Google Search, Google has stated that they index over 30 trillion individual sites. Obviously, this can also be very time-intensive. This is why much of the work of a search is the indexing, which can take place piecemeal and offline. By the time you search in Google, those trillions of indexes to websites already exist, and the service uses efficient algorithms to search those indexes. An additional expectation is support for fuzzy searches, where logically related words are also searched. You've seen this on Google Search when it suggests a search term if you've misspelled it, or when you search for bake, it might also hit on baker or baking. You can implement your own free-form text searching in Azure Cognitive Search. In this case, the items may be stored in a store like Azure Data Lake, and the search service then indexes those items. If you're using SQL Server or Azure SQL Database, you can actually store your documents to search in a table in the database, and the database can create the search index for you. The heart of any free text search system is the search index that makes it possible. So let's look at a few options you have for creating your search index. Microsoft offers Azure Cognitive Search, which used to be called Azure Search. Given a collection of documents, it will search them for keywords and index them. It can handle a variety of file types, including Excel and PDF files. Elasticsearch is another option, which is based on the well-known Lucene library. This is available on Azure as well as Google Cloud and AWS. And there's HD Insight's Apache Solr, which can also index a variety of file types, such as Word documents and PDF. These technologies build the index before you search. Once the index is created, you can use their APIs to make a request, sending in your search criteria. When you add new documents, these technologies can then re-index. The next consideration after what service will build your index is which data store you'll choose to store it. This list is going to look familiar because basically the services that perform the indexing can usually store the index. So you have Azure Cognitive Search, HD Insight's Apache Solr, Elasticsearch, or if you use Azure SQL Database, you can use its full text search features to both generate an index and store it in a table in the database to handle free text search queries. Now let's say you're looking for an appropriate free text search data store for your specific needs. What would you be considering? You should consider whether you want to host your service yourself on your own infrastructure or whether you want to go with a managed cloud service like Azure Cognitive Search. In most cases, it's easier and cheaper in the long run to have it managed for you. Will you know before you code what index schema you're going to be using? Some services allow you to define your own schema and some don't. You may need just full text search indexing, or you might want to have other data features such as aggregation. Make sure the data store offers the analytics you need, hopefully in the same package. And finally, be aware of your security needs and make sure that the data store you choose meets those criteria. In this video, I'm going to talk about a type of solution that's been more common in the cloud over the past several years, and something that I've personally worked on in the industrial sector for much of the past 2 decades. That is time series solutions. With the explosion of Internet of Things, or IoT, as well as Industrial Internet of Things, or IoT, management of time series data is bigger than ever. Time series data is organized by time. Each piece of ingress data contains a timestamp, which represents the official time associated to that data in charts and tables and in calculations. Data ideally arrives in an ordered stream, in order of time. In my case, I've worked on systems to collect time series data from IIoT devices out in the field. Timestamps and ordering can actually become complex, since the timestamp is usually determined at the device and not when the data arrives at the cloud. The difference is often small but can be significant. And occasionally data would come in out of order if it was delayed, so some ordering had to be done at the ingress. But these are fine details. With time series data, all data is inserted and not usually updated. Once data is brought into the data store, it's typically considered an official record of that data and therefore never changed. So to make this more concrete, what are some applications of time series data? Companies are currently attempting to train cars to drive themselves. The computer systems they use take in constant streaming data from their cameras. This real-time car data is time series data. Stock prices are another example of time series data. The one I'm most familiar with is sensors on industrial equipment. Much of the equipment used in industrial sites these days have sensors that send data to a central service for analysis. And your servers can generate their own performance data, which would be time series data, which could be analyzed to determine how to make your services more efficient. So what does time series data look like? And what do time series data stores have to contend with? Time series data is often high volume. I've personally designed systems to deal with devices that send several hundred values per second. The individual data points tend to be small, in the realm of a few kilobytes. But there can be a high ingress flow to deal with. NoSQL databases are great at handling this real time. There are often many data sources. As a practical example, I've worked on systems to collect data from hundreds of well sites or thousands of HVAC units spread across the globe. Time series data is really designed for telemetry data, such as what I've described, getting streaming data from actual devices. This data could be telemetry such as temperatures, pressures, or flow rates. The important thing to remember is that all this data is analyzed by time. Analysts are looking at a window of time and looking for patterns. For example, how much oil flow came from a field of well pads over the past 24 hours? And is this increasing or decreasing over time? How much energy did a solar panel farm generate during the hottest hour of the day? These are the types of questions that time series data helps answer. Some of the benefits of time series data are: organizations can determine how their assets are changing over time, and this often equates to money. For example, a solar farm might want to know whether the performance of their solar panels are degrading over time, so they know when to replace them. Time series data can detect changes right away and alert someone. Perhaps the pressure in an oil pipe suddenly rises above a threshold, and the manager for that plant can be notified via text. Time series data is well suited for predictive modeling. With enough data, machine learning or AI can analyze it and make predictions that can save companies real money. I can attest that there's an entire computer industry built around making such predictions in the industrial sector. With the rise of the Internet of Things, or IoT, time series data has really come into its own. In the IoT scenario, you have physical devices that are capable of streaming their telemetry live to a service, usually in the cloud. If you have smart devices in your home, those are IoT devices. For example, you may have a smart thermometer that sends temperature telemetry to the cloud. That data is collected and displayed in the chronological order according to its timestamp, which would be when the data was collected at your home. You may be able to go online and look at trends of your data in a chart to discover how you're using your heat. This can help you to spot anomalies. It can also help you predict what your future usage might be. The service does this by ordering the data by its timestamp, which allows the service to store it in the order in which it was received. Time is often of the essence when dealing with time series data. One application that almost always goes with time series solutions is an alerting system to notify the appropriate people as real-time as possible about anomalies. This is typically done as the data is streaming in, for it's at this streaming data layer that the system has the earliest opportunity to recognize those anomalies. Such systems look at sliding windows of time, such as a few seconds at a time, and perform simple calculations to look for anomalies that demand a notification for someone to act. For example, the manager of a wind turbine farm may get a text notification from the system when one of the turbines doesn't report new data for a minute. The manager can then take action and check on the turbine. As mentioned, time series data is often high volume and coming in fast, so time-efficient technologies need to be selected to handle that job. You need to consider how the system will store the incoming data in real time, or fast enough to not fall too far behind, index that data for efficient querying, query the data, analyze the data, and there are two aspects to this, both real-time analysis and offline analysis, and how the data will be effectively visualized. Now let's take a look at the architecture of a time series solution. We'll work our way from the ingress back to the analysis layer. As data flows into the service, say from IoT devices, it encounters the stream buffering layer. This may be an IoT hub or event hub in Azure, or some other buffering layer which receives the incoming data and buffers it so downstream processes can consume it at a regular rate. It's common for time series data to come in bursts rather than a steady stream, which is why this buffer layer is required, to avoid the service from being overwhelmed during data bursts. Next, you have a stream processing layer. This layer may look for anomalies and issue alerts. It may also run a machine learning service to look for patterns in the data. The time series data and optionally results of the processing go to an analytical data store, such as Azure Data Explorer, where it can be queried and displayed. So, to review what's involved in a full time series solution, you need data storage for when data is ingressed and waiting for further analysis. You have analysis tools, visualizations, and reporting for finding important trends and patterns in the data. You have an analytical data store, which serves the analysis and visualizations. And at the ingress, you need stream processing and stream buffering to handle and process the data real-time as it flows into the system. We'll finish up with requirements for time series data stores. Time series data stores are often normalized. The schema of the incoming data is usually known, so the data in the store is normalized to account for that schema. Consistency across concurrent writes is not applicable, since the system handles all writes real-time. Data is stored time sequentially, making it easily queryable by time window for analysis. It often contains multiple indexes to allow for efficient querying across several dimensions, such as filtering for time and temperature. The datum, being the ingested data points, are small. The telemetry is usually simple, such as a single temperature value. The data stores for time series are typically large, in the range of. So in this course, we've examined non-relational data workloads. We did this by exploring characteristics of non-relational data, using non-relational data versus relational data, non-relational data types, use of CSV and JSON files for non-relational data, and non-relational data stores, freeform search text, and time series solutions. In our next course, we'll move on to explore non-relational data services.